Hi everybody, this is Jazz from About Slingshots YouTube channel. In my previous video, which is called How Slingshots Actually Work, we studied the internal ballistics of slingshots. That is, we studied the forces, or variables if you want, which actually determine the exit velocity and exit energy of your ammo. And this happens at the very special point, which is halfway between your anchor point and the fork tips. This is the point where the pouch stops accelerating the ammo and ammo becomes a projectile, or it starts its free flight. And what happens during this flight is studied by external ballistics, and this is the subject of today's video. I'm not an expert in external ballistics, but I was curious enough and I had many open questions specifically related to slingshot, so that I had to read, research and learn about the subject all by myself. What I learned I want to share with you using as plain language as possible. All the background calculations for this video are done by my Slingshot Setup Designer, or SSD, which you can download for free from my Google Drive. The link is in the description below. It is not a perfect piece of software, there are some bugs too, but it does capture all of the most important variables related to slingshot ballistics. Let me introduce the standard set of parameters which has been used for the background calculations in this video. Draw power is 4.67 kilos. Active band length is 15 cm, draw length 75 cm, which means that the stretch ratio is 5. Elongation is 60 cm, 75 minus 15. The weight of the active band is 3.8 grams. The standard ammo which is going to be used in this video is 9.5mm steel ball with the weight of 3.55 grams. Fired under these conditions, this ammo reaches 65.26 meters per second and energy of 7.56 joules. Most shots will be done under 45-degree angle. Fork height is 1.5 meters, target height is 1.5 meters, target distance 15 meters, air temperature 20 degrees Celsius, air pressure 1 bar, humidity 50%, air density is 1.181846 kilos per cubic meter, and gravity is 9.8129 meters per square second. Of course, other parameters will be used too. Let me first make an overview of external ballistic topics, or if you want, the parameters which directly affect the shape, the range, the height and so on of your trajectory. So at this very special point where the pouch stops accelerating the ammo receives exit velocity and exit energy. Then your ammo is more or less aerodynamic, and this is measured with drag coefficient. Then your ammo has a silhouette or reference point, which is the area of the round ball which confronts the air. Then the shot can be done from this or that angle. Then the forks can be lower or higher from the ground. Then there is air density, which is in itself composite value of 3 parameters: air temperature, air pressure and humidity. And finally there is gravity. So let's begin. Exit velocity and exit energy are probably the most important parameters of the flight or external ballistics. Because, to put it this way, without velocity, without energy, your ammo is not moving. For me, exit velocity and exit energy, they represent the ending of internal ballistics process, and they announce the start of external ballistic process. And we shall have to deal with these two parameters in such a way as first we go one step back into internal ballistics and then we go on. Let us see first how exit velocity and exit energy are calculated, because this has huge implications on the trajectory later. So the first parameter is draw power. It goes directly into the calculation of exit velocity. Second, there is a total weight of the pouch, ammo and of rubber, which go into the calculation of exit velocity, or if you want separately, ammo, pouch and rubber. These 3 weights, they are added up and they go into the calculation of exit velocity. And finally there is elongation. If you remember, elongation is the difference between your full draw and the length of your active bands. However, we are not going to discuss elongation in this video, because whatever applies to the elongation applies to draw power and vice versa. For example, 10% more elongation is the same as 10% more of draw power. So there is no need to discuss this. Also, we are not going to change pouch weight and rubber weight, which means that as variables we have only ammo weight and draw power as inputs, and exit velocity and exit energy as outputs, and we shall see later the implications on target shooting, long-range shooting, on the trajectory, and so on. Now, part of the formula for calculating exit velocity takes draw power and divides it with total weight. And since in our case we don't play with pouch weight and rubber weight, we can only change ammo weight. And as you probably know from the basic math, when you divide fixed number with ever-increasing numbers, then the result is decreasing, like 4.8 kilos of draw power divided by 2, 3 and 4 grams, you get smaller and smaller number. Which means that when ammo weight goes up, velocity goes down. But also, if you have ever-increasing number and you divide it with a fixed number, like you have 4.8, 6.8, 8.8 kilo slingshot, and divide it with 2 grams, then the results are ever increasing. So, as the draw power goes up, velocity goes up. Then how energy is calculated? The first input is exit velocity, which we calculated a moment before, and ammo weight, but only ammo weight without pouch and rubber weight. And in this case, these elements are not divided, they are multiplied. Actually, ammo weight is multiplied with exit velocity, and as you know from the basic math again, if one of these or both of these variables increase, then the energy will increase too. Which means that velocity and energy behave completely differently, or they go in opposite direction as the ammo weight increases. But we shall come back to this later. Let us put now all these variables, ammo weight, draw power, exit velocity and exit energy, in a broader perspective. Here I have a table which in the columns show the ammo weight, 1 gram, 3, 5 and 7 grams. And here in the rows it shows draw power, 1 kilo, slingshot 3, 5, 7 kilo. And these are the velocities, see, in meters per second, calculated for each of these combinations. For example, 1 kilo slingshot and 1 gram ammo, the velocity is 49.44 meters per second. So on a graph this looks like this. These are the ammo weights and these are the draw powers. Now, if we read this first row, which means that we hold 1 kilo slingshot constant and we change the ammo weight, then the velocities look like that. Actually, velocities are decreasing as the ammo weight increases. Here. The second row, 3 kilo slingshots, is the same but on the higher level. Third row and fourth row for 7 kilo slingshot. Or you can put it this way. In one instance, for the 3 kilo slingshot, you have 1, 3, 5, 7 grams ammo in your pockets and 3 kilo slingshot. And then we see what the velocities are. Or if you hold the ammo constant, you have 5 grams ammo in your pocket and you have 4 slingshots with 1, 3, 5, 7 kilo draw power. And then we see what is happening here. But basically, as the ammo weight goes up, the velocity goes down. If you increase the draw power, the same thing happens, but on a higher level. Or if you hold the ammo weight constant, increasing the draw power increases the velocity. And just to remind you, this is the formula. And with energies, things look like this. Again, we have our ammo 1357 grams and our slingshots 1357 kilos of draw power. On the graph, this looks like this. Ammo weights, draw power. And we said, as the ammo weight increases for a given draw power, the energies increase. This happens with 3 kilo slingshot, but on a higher level, 5 kilo and 7 kilo slingshot on a higher level. Or, again, we have 3 kilo slingshot with 1357 grams ammo in your pocket, or you have 5 gram ammo in your pocket and you have 4 different slingshots. And finally, this is the formula. With this and previous slide, I made a small departure from the original slide where we spoke about how exit velocity and exit energy are calculated in order to show you the full territory of what is happening when we change the draw power and ammo weight. Because mostly in the rest of the video we are going to take the slice, either this one or that one, which means that we are going to change ammo weight or change the draw power, understanding that what happens here basically happens also here and here, but on different levels, so that you actually do not get lost. And here we are back to the original slide. We said, as the ammo weight goes up, velocity goes down. And as the ammo weight goes up, energy goes up. And it will be very interesting to see these two curves on the same graph. And we shall do this in this way. We shall say here, this first highest data of the velocity here on this graph is 100% and all the others are recalculated. This is also with the energy. This highest data is 100% and all the others are recalculated. Then on a percentage graph or 100% graph, they look like this. A very interesting picture, and I think that we should enlarge this and try to analyze it. So here it is again. Velocity as the ammo weight goes up and energy curve as the ammo weight goes up. And this point here looks like a very interesting point. To me, it looks like the illustration of how to put it. When the experienced shooters, especially hunters, when they say that for hunting you need more energy, even at the expense of velocity, like here. And for the target shooting, you need simply the velocity. So this could be target shooting side, and this could be hunting side. So what choices, for example, hunters have to make? At this point, a 6mm steel ball fired under 4.67 kilo slingshot. The velocity of this ammo is 55.56 meters per second and energy is 9.26 joules. If the hunter considers going to 8mm steel ball, then velocity drops to 50.2 meters per second and the energy goes up to 10.08 joules, or energy drops by 5.36 meters per second and energy goes up by 8.82 joules. Here on the target shooting side, things are more simple. Smaller the diameter of the ammo, which means lower weight, higher the velocity, the trajectory is more flat, and then the target shooting is easier. But these choices here, how small ammo, how large ammo, and so on, are not mathematical. They are basically personal and depending on circumstances. For example, I myself, I cannot handle any ammo smaller than 8mm in diameter, which is 2.5 grams. And on the hunting side, you do need power. And how much power you can handle is questionable. Of course, nobody is going to go hunting with a slingshot which is 4.67 kilos. Probably 6, 7, 8 kilo slingshot is good to go. And all these numbers then they are pumped up. Like 10 joules will become 12 joules for 8mm ammo. And as far as I know, people go with 10, 11, 12mm steel ammo or lead. So the choices are, how strong you are in order to manipulate a strong slingshot. Second, is a rabbit standing still, in which case you can afford lower velocities, or is jumpy, so you need to go for higher velocities, maybe less energies. But I myself, I'm not a hunter, so this is only my lamentation on the subject. Now, let us demystify to a certain degree this point. Let me clear the graph. So let's say that I do not want to consider the ammo less than 6 grams in weight. So I don't need this data on ammo weight, on velocity and on energy. I don't need this part of the graph also. So this data here becomes the highest data of velocity and it becomes 100%. And it is now here, you see 100% for 6 grams ammo. And all the other data are recalculated. The energy line stays the same. You see, this is 100%, it stays the same. It's already recalculated up to here. So our point moves to the new position, which means that this point is not an absolute point but a relative point. It depends on the scope of your choices. If you consider the ammo from 1 gram to 12 grams, then this point is here, of course, for the slingshot, which is 4.67 kilos. If you consider ammo from 6 to 12 grams, then it is here. Simple as that. Now let us see what do these considerations of ammo weights and draw powers have on target shooting. We shall have a target which is 15 meters away, whose center is 1.5 meters above the ground, and the forks are at a level of 1.5 meters above the ground, which means that our slingshot is pointed directly at the center of the target. Of course, in this way you cannot hit the target, because there is a drop. The trajectory looks something like this. But this is exactly what we are looking for. So, do you remember our graph where we showed the interplay of ammo weights and draw powers? Let us consider now this case, where we have one draw power, but for this one draw power we change the weight of the ammo. And in our case, the draw power will be 4.67 kilos, and these are the ammo weights. This is the level of the target, 1.5 meters, this is this line. And these two columns are where you hit or how much you miss. Of course, these two numbers have to add up to 1.5. And this curve, if you want, looks like this. Let me explain. For 1 gram ammo, so if you shoot 1 gram ammo with 4.67 kilo slingshot, then you are going to hit at 1.338 meters here, or you are going to miss the target by 0.162 meters, 60 centimeters. And this is for 12 gram ammo. You hit at 0.896 meters, and the miss is 0.604 here. This is pretty straightforward. It looks just like the graph that we have seen in the previous slide. For a given draw power, heavier the ammo, lower the hit. Now let us consider the second case. Again our graph. Now we are going to hold ammo weight constant and increase the draw power. Here you see these are the velocities, and as we increase the draw power, velocities go up. At any level of ammo weight, does not matter what we hold fixed here. And in the target shooting, it looks like this. We shall be shooting 9.5mm steel ball, and imagine that we have 10 slingshots, where the first one is 1 kilo only, and the last one is 10 kilo of draw power. And then we shoot this 9.5mm steel ball from each of these. So this is the level of the target, and these are the hits. As an example, the 10 kilo slingshot will fire this 9.5mm steel ball at a velocity of 82.63 meters per second, and it will hit below the target at 1.34 meters, which is here, or the drop will be 0.16. It will miss the target by 16 centimeters. Now, there are some interesting considerations here. Let us say that somebody considers 6 kilo slingshot, this one, which makes the drop of 22 centimeters. And then he or she considers going to 10 kilo slingshot. Of course, I'm exaggerating here. Nobody shoots 10 kilo slingshot, I think, but let us say. And goes after improvement in the drop, which is only 16 centimeters here. So, 6 kilo slingshot, the drop is 22 centimeters. 10 kilo slingshot, the drop is 16 centimeters, and improvement with additional 4 kilos is 6 centimeters. Now the question is, are these 6 centimeters of improvement worth of these additional 4 kilos of draw power? Again, the math cannot say yes or no. Some other parameters need to be brought in. For example, I cannot stretch even 6 kilos. My maximum is somewhere around 4 kilos slingshot, but somebody can. And then the question is it worthwhile? Is it worth it, these 4 additional kilos? For me, it would be, even if I could stretch 10 kilos, it would be easier to compensate the target for 22 centimeters than to go after additional 4 kilos. I think that this case is justified only if your doctor told you to exercise. For example, if you shoot 100 rounds a day, times 4 kilos is 400 kilos, I would say, of unnecessary power a day, or 2.8 tons a week, and about 146 tons per year. So this was target shooting, but what about long-range shooting? Let's consider this. We have ammo diameter fixed and we only change the draw power. And the thing is really very simple and straightforward, I would say. With 4.67 kilos, the 9.5mm steel ball is fired by 65.26 meters per second and it will reach 171.5 meters of range there. And if you shoot this same 9.5mm steel ball from a 3 kilo slingshot, it will reach 55.31 meters per second or 145.5 meters of range. So the situation here is really straightforward. Stronger the draw power or more draw power, longer the range. But if we now hold draw power fixed and then we changed the diameters of the armor and then see what happens with the range, then things become a little bit weird. Let us see what's going on. So I have the draw power now fixed, and then here I have armor of various diameters, specifically 3, 4, up to 12 millimeters in diameter, of course steel ball, and this is their corresponding weights. Then we shoot first 4.6 kilo slingshot with each of these armor, and then we shall see 3 kilo slingshot and 7 kilo slingshot and see what's going on. Now, normally we would show the trajectory in, I would say, a normal side view. That is, it starts like here, goes up and then reaches some range here. But now we are going to turn the whole thing like this. We are going to read the ranges here on the vertical axis, and here we are going to read ammo diameters. So we are going to get a curve which will show us how far each of these armor with various diameters will go down the range fired from these 3 slingshots. But before we go on, I would say that normally we would think that if the draw power is fixed, as we fire heavier and heavier armor, it will go shorter and shorter range. So the curve might look something like this. I think that we all expect something like this. However, for the slingshot of 467 kilos, like this, surprise, the curve which tells us something about the range of these various armor or various diameters looks like this. Let me get rid of this curve. Now, this line tells us that there is a point somewhere on this curve, and basically it is 8+ millimeters armor, which will go the longest range. All the others, like 6 millimeters, 5, 4, or 11, 12, and so on millimeter armor, will go shorter range. For 3 kilo slingshot, the thing looks the same, except on the lower level. And for a 7 kilo slingshot, the things are again same, but on the higher level. And I did some calculations, which tells me that the longest range for 4.67 kilos would be reached with somewhere around 8.7 millimeters steel ball, which is 2.7 grams of weight, and it will reach 173.53 meters. For 3 kilo slingshot, it will be 7.8 millimeter steel ball, which is 1.95 grams in weight, and it will reach 153.1 meters. And for the 7 kilo slingshot, it is 9.3 millimeter steel ball, which is 3.3 grams, and it will reach 192.92 meters of range. Let us now go back into our normal trajectory view, the side view, as I said, but not with these values, 7.8, 8.7 and so on, because they are a little bit, confusing maybe. Let us select here 6, 8 and 10 millimeters steel ball and see how far they go, but on a normal view. So here I have meters of the range, and here is the height. So the first steel ball that we fire is 6 millimeter steel ball, which reaches 158.1 meters of range. If we fire 8 millimeter steel ball, it goes, longer range. Normally we would expect it to fall closer to the original point, but it goes further down the road. It is 172.79 meters of range, and 10 millimeter steel ball goes 169.08 meters of range, more or longer range than 6 millimeter steel ball and shorter than 8 millimeter steel ball. So it's really interesting to see the left and the right side of these curves. Here on the left side we shall introduce the concept of the drop, and we shall speak about this later more, but the drop is the distance between so-called bore line or departure line and the point on the trajectory right beneath it. Basically, in practice, this means that you turned your slingshot or you directed your slingshot so that its angle is 45 degrees, as here. But no ammo will go at this trajectory. It always is pulled down by the gravity. So, a given distance, for example here, the drop is the difference between this point on the bore line and this point on the trajectory. So, the things on the left side, when the drop is in question, look quite normal. 6mm steel ball has a smaller drop than 8mm steel ball, and 8mm steel ball has a smaller drop than 10mm steel ball. Completely intuitive, completely normal, I would say. But on the right side, things are a little bit scrambled up, maybe, where 6mm steel ball has the shortest range, and 8mm steel ball has the longest range, and 10mm steel ball falls somewhere in between. You see, here is the place or the point, they are the points of the entanglement, if I can use this term now. Then there's a logical question, why is this so? Well, if I were a ballistic expert, I would know the answer, but I'm not. So I had to do some research. So this is our curve that we want to explain. Then I took the energy curve. As the ammo weight goes up, energy goes up, as we have seen before, and this does not explain this curve, maybe in the first part here. Then there is velocity curve, which explains this curve even less. Then there is a series of curves which more or less look like this. This is how the ammo weight goes up as the diameter of the ammo goes up. This is basically a cubic function because the volume of each of these round balls is calculated and then multiplied by the density of the material, in this case steel. Then the last concept that I could think of was basically the relation between the energy of each of these round balls and the surface of each of these round balls that confronts the air during the flight. This surface is called silhouette, and we shall speak about this in the next video. But basically, for the round ball, this is a cross-section, or it is equal to the cross-section of the round ball, which is basically area of the circle. And dividing these two values, energy with the surface area, should give me the number which tells me how many joules are per each square millimeter of each of these round balls. So I developed a following table. Here are the diameters and here are the respective silhouettes. You see, the diameter of 3mm has only 7.06 square millimeters of the area that confronts the air, while 12mm diameter ammo has 113 square millimeters that confront the air. Then I calculated energies for each of these round balls. See, for 3mm steel ball it's only 0.5 joules, and for 12mm steel ball it is 9.76. So when I divide energy with silhouette, I get this sequence of numbers. And then when I put these numbers on a graph, it looks like this. Very similar to our curve that we want to explain. Not completely the same, but very close. The difference might be attributed to air resistance and some other reasons, but I think that enough has been explained with this energy per square millimeter of the silhouette. Now let us go back to our graph. In real life, we have many levels of draw power at our disposal, and many types of ammo and their size. But for illustration purposes, we have this draw power and these diameters of steel balls. So, if there is a tournament round in target shooting, your best choice would be 6mm ammo because it has the lowest drop, allowing you easier aiming. When hunting is related, we are still on the left side of this curve. I think I called it a normal side. You will probably go for a trade-off between energy and velocity and go for 10, 11, 12mm ammo, where the drop is bigger, but the energy is enough to bring down the game. However, if there's a tournament, in the sense of who is going to send its ammo further down the road, it's a long-range shooting, then the things are completely different. The best choice of ammo is that one which has highest number of joules per each square millimeter of the surface area that confronts the air, and in our case it is 8mm steel ball. And one clarification here. We said that on the left side of this graph we had a normal sequence, 6, 8, 10 mm steel ball, 6 having smallest drop, 10 having biggest drop. And on the right side, this relation got scrambled up so that 8 mm steel ball had a longest shot, then 10, then 6 mm. So this was fired under 45 degrees angle, and this is it. Now this holds also about 30 degrees angle, 8, 10, 6. It does not hold completely for 15 degrees angle. Here 6 mm steel ball has a longer range than 10 mm steel ball, and does not hold at horizontal shot, where we come back to the normal sequence where 6 mm steel ball has the longest range, then 8, then 10. There's another interesting concept related to energies and velocities, and I would put it this way. Let's say that we shoot at a target which is 20 meters away. Its height is 1.5 meters, force height is 1.5 meters also, so we do more or less a horizontal shot. That is, we elevate a little bit the slingshot in order to hit the target. So the question is, what is the velocity and what is the energy at this point, the point of impact, which we can call terminal velocity and terminal energy, in relation to the original or exit velocity and exit energy? That is, how much of the velocity and of the energy various armor of 6, 8, 10 millimeters and so on retain. And I can put it like this. I arbitrarily selected 9, 10 and 11 millimeter steel ball, and their respective velocities under our standard set of parameters are 68, 62, 57 meters per second. And on a graph it looks like this. And terminal velocity at these 20 meters target are 52, 50, 47, and it looks like this. Actually, we read this graph in this way. These are exit velocity and terminal velocity for 9 millimeter steel ball. This is here. And this is for 10 millimeters and this is for 11 millimeters. And then the question is, what are the percentages of the terminal velocities of these three armor in relation to their exit velocities? This is this calculation, and this is how it looks like. You see, no matter that 11 millimeter armor has the lowest exit velocity, it retains in percentage highest level of velocity, which is 82.9 in this case. More than 10 millimeter steel armor, more than 9 millimeter steel armor. When energies are related, the thing looks like this. These are the calculated energies. You see, for the 11 millimeter armor we have the highest level of energy, 8.98, and on a graph it looks like this. Terminal energies look like this, and then we also read them for 9 millimeter steel ball, exit energy and exit energy and terminal energy, then for 10 millimeters and then for 11 millimeters. Then the percentage of each of these terminal energies looks like this. This simply means that heavier armor retains higher percentage of both of velocity and of energy than any other smaller or lighter armor. And the last concept I would like to discuss in this video, and I promise the last concept, is how the setup is transferring its energy onto the armor. And how does it look like for various weights of armor? So let us say that this is the energy of a setup. Our standard setup has, if I remember well, somewhere about 22 joules of energy. And then there's a small armor, and it's fired. Then you see, symbolically, this small armor takes this small portion of energy of the whole setup, and the rest is the energy which is spent on the setup itself. This happens, for example, when you have excess energy, when you have small armor, and your pouch and rubber, they go very fast over the fork tips, and then come back and slap you on the hand. So you get a hand slap. Larger armor or heavier armor takes more of the energy, symbolically shown like this, and still the bigger armor takes again much more energy like this. And this from here to here and from here to here and from here to here is basically the energy which is remaining energy in the system. I intentionally put here 50% mark because we shall need it on the following graph. And the following graph should tell us how this transfer of energy from the setup onto the armor looks like. Here I have armor weights from 1 gram to 14 grams. And the energy of the setup is the same in all instances. 22.73 joules. This is 50% of this setup energy, 11.37 joules. This is the energy of the ammo of 1 gram, 2 grams, 14 grams. And this is the percentage of the energy that ammo takes out of the total energy of the setup. And on the graph this looks like this. This is energy of the setup. This is 50% of the energy of the setup. And this is how the curve which explains the percentage of the energy that ammo takes as the ammo weight goes up looks like. You see, in order to reach 50% of the setup energy, ammo needs to be 14 grams in weight and then takes about 50.02% of setup energy, which is 15.04 millimeters diameter steel ball. So in the final analysis, in order to avoid hand slap, you have to go for heavier and heavier ammo. But then the velocities are lower and lower. So it's a constant trade-off which the math itself cannot solve. But you need to bring in outside parameters to solve it. For example, can you live with lower velocities? If yes, then it's okay. But if you cannot, then maybe change the way you tie your setup or wear a glove. This brings us to the end of part 1 of this video, in which we covered only exit velocity and exit energy. In the next video we are going to cover all the other parameters that influence the trajectory. Thank you for watching, and don't forget to subscribe because part 2 of this video is coming.